So we just covered the first of our three main examples, or three main results for multivariable calculus. And our first one was called Green's theorem. And Green's theorem gave us a way to convert a single integral, a line integral actually, to a double integral over a region. Now the next result is called the divergence theorem, and we're going to go over this one just a little bit differently because we're basically going to skip right to the result. So what I mean is the problems that you're actually going to see about the divergence theorem are going to give you this double integral, what you would really see, like on a test or probably on your homework in your class. They're actually going to give you a double integral and ask you for something called the outward flux of a vector field. Since we're just practicing and just sort of introducing this for the first time, we're actually going to focus on this computation, this triple integral computing the divergence of a vector field. So again, kind of like Green's theorem, now we have these two, I guess, two different parts of one volume. So there's the volume that's enclosed by this surface, and then there's actually the surface, so this S just refers to just this surface here that encloses this volume. So the volume is like everything that's here on the inside, and then the surface is just this curvy part on the outside. So if we have a vector field and all of these other things are met, so f, g, and h, these three component functions have continuous partial derivatives, blah, 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 like basically everything is friendly, and you have this outward unit normal, then this dot product of the vector field, or the vector function with the outward unit normal, is the same as converting this to a triple integral of just the divergence. And this thing is called the divergence theorem. Now, again, it seems a little bit counterintuitive if someone gives you a double integral to convert it to a triple integral and then compute it, but it turns out that computing the divergence, the triple integral of the divergence, can oftentimes be pretty simple. These are going to be really, really simple computations. Now, before we do this, let me just put a note here. If you don't remember what the divergence is, let's say that we have some vector field with three component functions, f, g, and h, and these component functions are of variables x, y, and z. Then we say the divergence of f is just the three partials added together. So the first component with respect to x plus the second component with respect to y plus the third component with respect to z. And this is going to give us either some function, or if we evaluate it at a point, it's going to give us a number. But really, this is just going to give us some singular expression in three variables, but just one expression, and that's going to go here. And we're going to evaluate that over a triple integral. So let's do a couple of examples. Now, as I said, we're just practicing the computations. What a problem like this would really ask you is not to find the triple integral of the divergence. It would be to find the double integral of the function dotted with the normal vector. So it would ask you for this over the surface, and you're going to convert it to this. But we're just going to start with kind of the result. We're going to sort of skip ahead a little bit and just see how these triple integrals of divergence are friendly. So our vector field in this case is a pretty simple one, 0, 0, z. So let's start by finding the divergence of f. So that's going to be the partial with respect to x of our first component, which is just 0. So partial with respect to x of this one, plus the partial with respect to y of our second component, which is also 0, plus the partial with respect to z of our third component, which is z. Now obviously these two don't mean anything to us, but the partial with respect to z of z is just 1. So here is our new integrand, and this goes here. And you'll see this first example demonstrates how easy these examples can be. So this triple integral just became kind of nothing. I don't even have to write this 1 here. It can just be the triple integral of this little volume element. Now, essentially, when someone asks you to find the triple integral of just the volume element, like there's nothing there, it really just means the volume of the solid, whatever solid we're talking about. In this case, the solid that I'm talking about is the sphere x squared plus y squared plus z squared equals a squared. So this is like the radius of the sphere is in this case a, and then the radius squared is a squared. So the formula for the volume of sphere is 4 pi r cubed, so in this case 4 pi a cubed over 3, and we didn't even have to do any computation. Now, what the problem really would have asked you is to find something called the outward flux, which is this, and you would have converted it to this triple integral of the divergence, but we're just skipping ahead to see how easy this can be, and that made our computation really simple. So let's go on to the next one. We'll do 2 more examples of sort of applying the divergence theorem. So the next one says, use the divergence theorem, and which I'm already using for you by giving you this, to find the triple integral of the divergence. So now here is our vector field, 2x, 3y, and then z squared, over the unit cube. So the unit cube is going to have vertices 0, 0, 0, 1, 0, 0, so 1 in the x direction, and then nothing in y or z. 0, 1, 0, so over here, and then 0, 0, 1. So basically we're going to build a cube with those corners, and it's going to look something, this is hard to draw on a little tablet thingy, but it's going to look something like this. So we're integrating this vector field over this unit cube, one step in every direction. So the divergence theorem would have actually asked you to find the double integral over the surface of this cube of the vector field dotted with its outward unit normal, which is just like this little unit vector outward in every direction. And the way that they say that is find the outward flux. But we're going to skip ahead, and we know that divergence theorem says don't do that. Just convert it to a triple integral and use the divergence instead. So let's find the divergence of this vector field. And then we'll actually take this triple integral. So the divergence is just the partial with respect to x of 2x plus the partial with respect to y of 3y plus the partial with respect to z of z squared. And this is going to be over some volume. So in other words, I'm going to integrate over the cube, triple integral. Now this is a unit cube, so I don't even have to think about kind of what I'm doing here. Every single one of these variables is going to go from 0 to 1, 0 to 1, 0 to 1. Everything goes from 0 to 1. It's over the unit cube. Partial with respect to x of 2x is just 2. Partial with respect to y of 3y is 3. And partial with respect to z of z squared is 2z. Now I just have to decide on my order of integration, and since the z is the only variable, I'm going to get rid of that one first and integrate with respect to z, and then I'll integrate with respect to y, and then with respect to x. So you've probably already put this together, but this integrand is the same as just 5 plus 2z. That's what I'm really integrating. So my first integral with respect to z, the 5 is going to integrate to 5z, and the 2z is going to integrate to z squared, and I'm going to evaluate this from 0 to 1. And then I'll go back and integrate with respect to y, and with respect to x. Now 0 kills the whole thing off, so it's really just plugging in 1, and this is going to be 5 plus 1, so just 6, and this becomes a double integral from 0 to 1 on both of just 6. Now when I integrate 6 with respect to y, that becomes 6y from 0 to 1, which is just 6. And then I'm going to integrate that from 0 to 1 with respect to x, which is again just 6, and that's my answer. So even though the original problem would have asked me to compute a double integral, and it is sort of counterintuitive to say I'm gonna bump this up a level to a triple integral. It seems like I would be complicating my calculations, but actually the divergence can sometimes make this so simple that even though we have to end up integrating 3 times, it still is a much simpler computation than having to I don't know, find the outward unit normal, dot these things together, integrate over the surface, which would have made 6 different integrations, right? Because over each surface, we would have had to integrate 6 times to integrate over a cube. Turning it into a triple integral and integrating one very friendly volume turned out to be a much easier way to do that problem. Okay, so last one, this one will be the most complicated because we will have to convert to cylindrical coordinates at a certain point, which are just pretty much exactly the same as polar coordinates. So r is the square root of the sum of the squares of x and y. Tangent of theta is just y over x, and then cylindrical coordinates just adds in this third conversion, which is not even really a conversion at all, but it just basically puts a height component in there. So everything is the same as polar, and then you just add height. So the last one says, use the divergence theorem to find the triple integral of the divergence of this vector field across the surface of the region that is enclosed by the cylinder x squared plus y squared equals 9, which is like this circle of radius 3, and the planes z equals 0 and z equals 2. So it's basically like integrating over this cylinder of height 2. Perfect cylinder that I just drew. So let's find the divergence of this thing, and then we'll integrate in cylindrical coordinates. So the divergence is the partial with respect to x of this first component, which gives us 3x squared, the partial with respect to y of the second component, which is 3y squared, and the partial with respect to z of the third component, which is just 2z. And now I'm going to convert to cylindrical coordinates before I keep going. And the reason that I'm going to convert to cylindrical coordinates is, first of all, because this is a cylinder. Despite my drawing, it is a cylinder, so that sort of suggests that cylindrical coordinates would be perfectly appropriate here. And then also I have this 3x squared plus 3y squared, which would give me 3r squared. And then notice 2z, well, z just converts to z, so that actually doesn't change at all. And dv converts to r dz dr d theta. And if you watch the video for Green's theorem, there was a quick explanation at the end about why a volume element, or sorry, an area element, dA, converts to r dr d theta when you're in polar. And it's exactly the same reason that there's this little extra r in cylindrical coordinates. So let's set up our limits. Now the first integration is going to be with respect to z. And z, in this case, goes from 0 to 2, just because in the problem it says we're starting at z equals 0 and ending at z equals 2. R is our second integration, and our radius is going to go from 0 to 3, because we're integrating over this cylinder of radius 3. And then, since we're going all the way around the cylinder, theta goes from 0 to 2 pi. So let's write this out one more time and then actually start the integration. 0 to 2 pi, 0 to 3, and then 0 to 2, and our actual integrand is 3r cubed when I distribute this r, plus 2rz. And then dz is the first one, dr is our second integral, and d theta is our third. So integrating with respect to z, so basically just covering this very first integral, integrating with respect to z gives me 3r cubed z for the very first expression there, plus Now r is a constant, 2z integrates to z squared. So 3r cubed z plus z squared, and I'm going to integrate this from 0 to 2, which, and everywhere when I say plugging in, it's plugging in for z, right? Because our first integral is with respect to z. Now 0 kills the whole thing off, so really 2 is the only, 2 is the only important limit to plug in. And that becomes 3r cubed times 2, or in other words, 6r cubed, plus, and then when I plug in 2 for z squared, it's plus 4. So our second integral is going to go from 0 to 3 of 6r cubed plus 4, and this one is with respect to r, and then I'll get to my theta integral in a second. So that's going to be 6r to the 4th over 4, or in other words, 3r to the 4th over 2, plus 4r. I'm just going to simplify that real quick. And we're integrating from 0 to 3. So again, 0 doesn't really do anything there. But the 3 is going to give us, oh, holy cow, 3 to the 4th is 81, times 4 is 243 over 2, plus 12. And then, let's see, so let me simplify that before I go on. 243 over 2 is not so friendly. And then plus 24 over 2, which is going to give me, what, 267 over 2? I know that my answer is supposed to be pretty bad in the end, so let's go with that. And now I'm going to do my last integration. Hopefully I haven't made any terrible typos. My answer is supposed to be 279 pi, so we'll see if we get there. So now I'm integrating from 0 to 2 pi. Oh wait, yeah, no, I'm not going to get there. Okay, 267 over 2. We'll figure out what we did wrong here. And when I integrate that, this is going to become 267 over 2 times 2 pi, and that's just going to become 267 pi, and the answer is supposed to be 279 pi, so I messed this up somewhere. 3 to the 4th really is 81, correct? 81. And then times 3 is 243, so this is right. Over 2. And I divided by 2 there and divided by 2 there. Okay. So let me see what I'm doing wrong here. And this was 6r cubed plus, oh, because I dropped the r. That's why. This should be 4r. 6r cubed, 3r cubed, z. Yes. Okay, right, because 2z integrates to z squared, but then there's still an r there. So there's an r here, so there's an r here over 2, which makes this 2r squared, fixing the problem. Makes that 2r squared, which makes this, instead of a 12, that makes this 24. And that makes this 48 over 2, which still doesn't make this 279, does it? I'd really rather not pause this video and do this entire thing again. Let me write this down. The answer is supposed to be 279 pi, and I'm sure you've all gotten there. But that is not what I'm... No, because I... There we go. Okay, 2r squared when I plug in 3, r squared is 9, times 2 is 18 on try number 3. 18 is 36 over 2, and that gives me 279 over 2. So then when I integrate 279 over 2, this becomes 279. This becomes 279 pi. Perfectly executed example, as always. At this point, you probably don't want to hear any more from me about this. At this point, you can either go on to the next video, which is about Stokes' theorem, which is sort of like, of these 3 results, there's Green's theorem, divergence theorem, and Stokes' theorem is by far the most important. Like, Stokes' theorem is sort of your first introduction to some, first of all, really high-level math. Like, there's no way to go over the proof of Stokes' theorem in class because it's just too complex. And the result is really, really cool. So you can go on to the video about Stokes' theorem, or you are ready for exercises 5 through 7, which are all about the divergence. So a couple of the examples that you'll be doing actually ask you to compute both of these integrals, so the double integral and the triple integral. And you'll just verify that these two things are the same. And as you're going over these, think about which of the computations is easier. Because divergence theorem, the whole point is that someone says, here's what we really want to know, and your job is to convert it to a triple integral and compute it that way. So as you're going through this, think about whether it really does make sense to convert it to a triple integral when you start with a double one, and whether or not that makes your life easier.